The problem statement tells us that we have a quadrilateral ABCD and angle DAC is congruent to angle DBC, and we know that the ratio of the area of ADB over ABC is 1/2. And then we let O be the intersection of BD and AC, and then they give us the side lengths that AD is 4, BC is 6, B is 1, and we want to find the area of the quadrilateral. So before we start the problem, we see that the fact that we have DAC equals DBC angles that the quadrilateral is cyclic, so we can inscribe the quadrilateral in a circle and use the properties of the circle. And the first thing that we notice here is that we have that triangle ADO is similar to triangle BCO. This is obviously by AA, as the problem gives us that those two angles are equal, and obviously by vertical angles, these two are equal. So then we know that the ratio of their sides is 4/6, which is 2/3. So then we get that AO is 2/3. And if we let OC be X, then OD is 2/3 of X. Now, we now want to use the fact that we know the ratio of the areas of ABD and ABC. And since this is a circle, angle ADB is congruent to angle ACB. So then this makes a good candidate of using the sine area formula, which gives us that the area of ADB is equal to 1/2 times AD times BD times sine of angle ADB, and then area of ABC is 1/2 times AC times BC times sine of ACB. And then since angle ADB and angle ACB are the same, when we divide these, we just cancel the signs, also cancel 1/2, and we know that this is equal to 1/2. So then this yields that AD times BD over AC times BC equals 1/2. And then from this, we plug in values and get that 4 times BD, which is 1 plus 2/3 X, over 6 times AC, which is equal to 2/3 plus X, is equal to 1/2. Then this gives us that 4 plus 8/3 X is equal to 2 plus 3X, and this yields that X is equal to 6. So then we get that OC is equal to 6 and OD is equal to 4. And now we have a lot of side lengths in the quadrilateral, and we can try to find the area. But first we see that what's interesting is that triangle OBC and triangle ODA are actually isosceles triangles. And this makes finding sine of angle BOC really easy, as then if this is OBC, then this is 6, and then we want to find the sine of that. This is 6 and this is 0.5. Then obviously sine of angle BOC is equal to square root of 36 minus 1/4 over 6, which is equal to square root of 143 over 12. Okay, and then from here we see that we can easily find the areas of every one of these triangles: ABO, BCO, COD, and AOD by just using the sine area formula, but when we're doing that, we can use the fact that like sine of BOC is equal to sine of AOB is equal to sine of AOD is equal to sine of COD, and then if we like write all the areas out, we get that the entire thing, or ABCD, is equal to 1/2 times sine of angle BOC times AC times BD. So this is equal to 1/2 times root 143 over 12 times sine of times AC, which is equal to 20 over 3, times BD, which is equal to 5. Cancel. And then, sorry, 3. And then we get that this in all is equal to 25 root 143 over 18, which, and then this, adding 25, 143, and 18, we get that this is equal to 186.